Hello everyone, my name is Eric Xie.
And my name is Chen Yang.
The project we are presenting is RSA timing attack. RSA is widely used for secure data transmission. The name of RSA is made of initial letter of three designers' username, Fast, Shamir, and Admin. The power of RSA is in its public and private key pair algorithm. The key pairs are strongly linked but very difficult to crack. One use case of RSA is a user can publish a public key, then anyone can use that public key to send a secure message back to the user, and only the user's private key can decrypt the message. As a result, delivering the encryption key to another is no longer an issue, because we can only send the unsecure public key out, and the key for decryption is always secure and hidden by the RSA algorithm. Another very common use is generating a certificate or digitally signing a message to prove the message is original and is from the trusted party. A user signs the plaintext using the private key, then attach the ciphertext as a signature to the end of the message, so no one else can change the plaintext. Otherwise, the signature won't match. Then the party that wants to check the signature, they can download user's public key, aka certificate, from a trusted site. Then everyone can verify the message's signature without using the private key. Although the private key is hidden locally and never been sent out, does that mean it is secure? Our project is trying to show if we could compromise the private key easily and quickly. We used Xilinx FPGA board to implement our RSA core and control logic. We used a PC to communicate with FPGA via UART serial port. The method is called timing side channel attack. Based on the input, the time needed for calculation will be different. For example, calculating 3 times 5 is much faster than calculating 123 times 446. We used our implementation on the FPGA board to collect the timing information of how long the RSA takes to finish encryption. Then we write a program on PC side to read the data out and analyze it. We want to see if we could find a link between the time and the private key used. To do the key guessing, we measure how many cycles it takes to encrypt one plaintext using the key. Then we guess that the bit of interest is 1, and we measure the cycle count. Then we guess the bit of interest is 0, and we measure the cycle count for that guess. We repeat this 8,000 times to generate large sample size. For each guess, we calculate the variance and go with the guess that will yield the closest variance to the actual key. Then we move on to the next bit. Here is an example of trying to guess the 4th bit. The blue graph is the distribution of cycle count when the actual key is used. The green graph is the distribution when we guess 0. The orange graph is the distribution of when we guess 1. We calculate the variance of each guess distribution and compare to how close it is to the original key.
Hi, my name is Chen, and I'll go over our FPGA implementation and the data that we've collected. We first wrote a GUI in MATLAB to communicate with the FPGA. This allows us to send the key to the FPGA core for testing. It would also store the cycle counts that the FPGA reports back. The attack core will use the key to encrypt data generated by a pseudo-random number generator. As the encryption is running, the counter is counting the clock cycles. Once the RSA core indicates that it has finished, the counter stops and the clock cycle count is sent back to MATLAB. This table shows the different variances calculated when running each guess key against 6 different 32-bit RSA keys. According to our algorithm, we first compare the variance of 0001 with 0011 as highlighted in red. 0011 has the higher variance, so the second bit is 1. Then we compare the variance of 0011 to 0111, which is highlighted in blue. 0111 has the higher variance, so the third bit is 1. This is incorrect, and further examination shows that the algorithm will always guess 1 as the next bit. Then we shifted our focus to guessing the 4 most significant bits. One thing we noticed was that the variances for some of the guess keys were exactly the same as the variance of the actual key. By only selecting the candidates with the exact same variance values, we can reduce the search space for a brute force attack. For example, on average, there are 3 candidate keys that have the same variance as the actual key. Having 3 possible values for the 4 most significant bits, and knowing that the least significant bit is 1, we can reduce the search space by 90%. We also noticed that increasing the guess bits from the 4 most significant bits to the 8 most significant bits did not reduce the search space any further. Thus, we've managed to show that timing data leaked by RSA implementations is a possible attack vector. Attempting to guess the least significant bits of the key didn't have any meaningful results. However, we noticed that by attacking the most significant bits, we could significantly reduce the search space for a brute force attack. One area of further work is to reduce the search space even further by only trying prime numbers. Thank you.